The law of mass action, or the ratio of concentrations in a chemical reaction. The derivations from the previous video are the justification for the law of mass action. The law of mass action is a mathematical description of the concentrations of reactants and products for a reaction that proceeds in both the forward and reverse direction. For the reaction where X moles of A reacts with Y moles of B to form Z moles of C and W moles of D, under equilibrium conditions, the equilibrium constant K is equal to the concentration of products over the concentration of reactants, which is equal to the concentration of C to the zth power times the concentration of D to the wth power divided by the concentration of A to the xth power times the concentration of B to the yth power. This equation is called the equilibrium expression. If a reaction is taking place in the gas phase, then there is no gas phase concentration for those reactants and products in the liquid and solid state. So those concentrations are taken as 1. If the reaction takes place in the liquid phase, i.e. solution, then the solid reactant and product concentrations are taken as 1. The take-home lesson is concentrations in the reacting phase only are used in the law of mass action. Typically, concentrations are taken in molarity, moles per liter. K, however, is usually expressed as a unitless number. The technical details of why this is unitless lies in terms of a concept called activities and is beyond the scope of this course, but it is reintroduced in analytical and physical chemistry courses. One of the limiting reagents for growing foods is the element nitrogen. While there are nitrogen-fixing bacteria that live in the roots of some plants, most plants are not limited by water, light, or carbon dioxide, but by a source of nitrogen for protein and other biological molecule synthesis. One of the great developments in chemistry is the reduction of dinitrogen to ammonia for fertilizer, the Haber process. Nitrogen from air and hydrogen from syngas process are united at high temperature to form ammonia. This is an equilibrium reaction, and the equilibrium constant K1 is equal to the concentration of ammonia squared divided by the concentration of nitrogen gas times the concentration of hydrogen gas cubed. We could just as easily have written the equilibrium equation multiplied by 2. Then the equilibrium equation would be 2 moles of nitrogen reacts with 6 moles of hydrogen to produce 4 moles of ammonia. The resulting equilibrium expression would be K4 is equal to the concentration of ammonia to the 4th power divided by the concentration of nitrogen to the 2nd power times the concentration of hydrogen to the 6th power. When we multiply the equation by 2, it is the same as taking the square of the equilibrium expression and square of the original equilibrium constant. We could just as easily have written the equilibrium equation divided by a half. Then the equilibrium equation would be 1/2 mole of nitrogen reacts with 3/2 mole of hydrogen to produce 1 mole of ammonia. The resulting equilibrium expression would be K2 is equal to the concentration of ammonia divided by the concentration of nitrogen to the 1/2 power times the concentration of hydrogen to the 3/2 power. When we multiply an equilibrium equation by 1/2, it is the same as taking the square root of the equilibrium expression. You should work through this to convince yourself it is true. And lastly, we can exchange the products with the reactants. So when one writes the equilibrium equation in reverse, in this case 2 moles of ammonia decompose to form 1 mole of nitrogen and 3 moles of hydrogen, the equilibrium expression is K3 is equal to the concentration of nitrogen times the concentration of hydrogen cubed divided by the concentration of ammonia squared. The relationship between K1 and K3 is that 1 over K3 is equal to K1. When we exchange products for reactants, then the new equilibrium constant is 1 over the old equilibrium constant. When one has an equilibrium expression, then one can determine the equilibrium constant from concentrations. Let's look at the decomposition of phosphorus pentachloride to phosphorus trichloride and chlorine gas as represented here. Now, suppose we have a 1 liter bottle which at equilibrium has 2.35 moles of PCl5, 0.65 moles of chlorine gas, and 0.65 moles of PCl3. What is the equilibrium constant for the reaction? Well, we need the equilibrium expression and then calculate concentrations of products and reactants and substitute in. So here is our equilibrium equation. Now we can write the equilibrium expression as K, the equilibrium constant, is equal to the concentration of PCl3 times the concentration of chlorine divided by the concentration of PCl5. So the concentration of PCl5 is 2.35 moles of PCl5 divided by 1 liter volume equals 2.35 molar. For PCl3 and Cl2, they each are 0.65 moles divided by 1 liter volume to get 0.65 molar. Now, substituting into the equilibrium expression, K equals 0.65 molar times 0.65 molar divided by 2.35 molar. So the equilibrium constant is equal to 0.18. Thanks for listening.